Hello everyone. We are starting the second half of our course, that is detection theory. We'll be using volume 2 of Stephen Kay's book. The specific chapters that we will cover include chapter 1, of course, introduction, chapter 2, 3, 4, 6, 7, 8, and parts of 9. Now, what is detection theory? So recall that parameter estimation problem essentially stands for finding a mapping from our sample space to our parameter space. We can define the detection problem as a special case of an estimation problem in which the parameter space only takes countably many finite values. We will come back to this later, so just to start with, keep this in mind. We can consider detection as a special case of the estimation problem, and that's partly the reason why we have started with the estimation theory. Okay, so the topics that we are going to cover, we will start with the Bayesian approach, since we have just finished covering the Bayesian approach to estimation, Bayesian risk theory, and detection and classification problems. Next, we will focus on the frequentist approach to detection problem and specifically cover Neumann-Pearson detection. We will look into recovering signals embedded in Gaussian noise, cover matched filtering, etc. And next we'll look into what's called the composite hypothesis testing problem within the frequentist approach. For the Bayesian approach, whether we have a simple test or a composite test would not make any difference. The theory applies to all different types of tests in a straightforward manner. But we'll see that that's not the case for the frequentist approach. So we will look into the composite hypothesis testing as a special problem. Cover the generalized likelihood ratio test, also known as GLRTs, a very widely used practical approach to detection problems when we have some unknown parameters in the detection. And finally, we will cover constant false alarm rate detectors. Alright, so what will this lecture cover? We will cover some notation and terminology. I will define what a hypothesis testing is, different types of hypotheses, different types of tests, test function, decision rule, and decision regions, and finally touch upon the error analysis. How do we quantify the performance of detection or a classification problem? Now first, the hypothesis testing. Detection, of course, is a term used in signal processing. Essentially, it's a term coined by radar engineers in early 1940s. It's an application of what is called hypothesis testing in statistical decision-making to signal processing problems, of course. Now, the setup that we'll be using is similar to the one that we use for estimation. Cap X will denote the random variables or vectors, and fancy X will denote the sample space in which we have the realizations of our random vector X. Theta is the unknown parameter, and depending on whether we are in the frequentist approach or Bayesian approach, we will be using F sub theta X, or the conditional product of X given theta is the PDF of X. Alright, so in hypothesis testing, in the simplest case where we have two hypotheses, we start with two distinct hypotheses on the parameter theta. Okay, so in one hypothesis, the parameter theta belongs to this parameter set sub 0 and pound 0, let's say. In the alternative hypothesis, theta belongs to another set, pound sub 1. Okay, now these two sets are disjoint, so their intersection is empty set, and the union of these two sets form the entire parameter space. And our task is to decide whether theta belongs to the pound sub 0 or pound sub 1. Okay, and we will do that based on the observations we have in hand. So we have a set of observations x1 through xn, and we have to decide which parameter best describes the data, okay, or rather which of the underlying PDFs which depend on theta describe the data that we have in hand. Okay, so notation that we will be using is fancy H for the hypothesis. So H sub 0 hypothesizes that X has the PDF F of theta X, where theta belongs to this parameter space pound sub 0. And hypothesis 1, on the other hand, hypothesizes that X actually has a PDF F of theta X, where theta belongs to the parameter space pound sub 1. Alternatively, we can write this problem, we can state the problem as hypothesis 0, theta belongs to this pound sub 0 set, or hypothesis 1, theta belongs to pound sub 1. Okay, all right, so those are equivalent. So to look at an example, suppose we observe x of n, and x sub n comes from a Gaussian distribution with mean theta and variance 1. We don't know whether theta is 0 or 1. We can state this problem, hypothesis testing problem, as x having a Gaussian distribution with 0 mean and unit variance, or alternatively x has a PDF which is Gaussian distribution with mean value 1 and covariance being an identity matrix. All right. So of course, alternative way of stating that would be the same problem, would be that H sub 0, the hypothesis 0, the theta, the unknown parameter theta is equal to 0, and hypothesis 1, the theta is equal to 1. Okay, so this will be a classical problem that we will see throughout the detection theory part of the course. Typically, theta being 0 means target is absent or signal is absent or there is no tumor. Theta being 1 means target is present or signal present, etc. Okay, so to see that, for example, we can write x of n as theta plus noise, where noise has 0 mean and unit variance. Okay, so we see here how theta represents the target or the signal or tumor, whatever. Okay, all right. Okay, so further on notation and terminology, we have already talked about it. Okay, so now we are going to define in the binary hypothesis testing a null hypothesis, and the null hypothesis typically means we were expecting something interesting to happen and that didn't happen. For example, a target was expected and there is none, so target absent. And typical notation used for null hypothesis is H sub 0. Alternative hypothesis is that the interesting event took place. It's also called alternative hypothesis and denoted by H sub 1. For example, target is present. Okay. Now, so we have defined binary hypothesis where theta belongs to either one of the sets. We can extend it to what's called M-array hypothesis or multiple hypothesis testing problem, where our parameter set, pound, is now decomposed into M disjoint sets. M disjoint sets. Okay, so these pound sub I and pound sub j are disjoint, so they are mutually disjoint, and union of these sets form the parameter space. Okay, so the ith hypothesis in that case is that theta belongs to pound sub I. Okay, this is also equivalent to say that the observations we have in hand X comes from a PDF f of theta x, where theta belongs to pound sub I. Okay, again, binary hypothesis testing, we can have tumor present, tumor absent problem. In the M array problem, typically also known as the classification problem in signal processing in electrical engineering, we have more than two hypotheses. A typical example is you have already detected a tumor perhaps, and now you want to classify what type of tumor it is. Is it a benign tumor, malignant tumor? If so, what stage is the malignancy, etc.